Tonight, we're going to talk about Saturn, the planet everyone recognizes, the one with the rings, the one that ends up on every astronomy poster and every classroom wall. And here's the thing nobody tells you. Behind that beauty is one of the most extreme, most violent environments in the entire solar system. Winds so violent, they've never once stopped in 4.5 billion years. Storms that swallow entire planets. Rings that are disappearing right now and will eventually be gone forever. By the end of tonight, you're going to understand why the most beautiful planet in the solar system is also the scariest one. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Saturn is the sixth planet from the Sun. It orbits at an average distance of roughly 886 million miles. That's nearly 10 times farther from the Sun than Earth is. The light you see reflected off Saturn right now left the Sun about 80 minutes ago. When you look at it in the night sky, you're seeing a world almost 1 billion miles away. And yet, for all that distance, it's one of the 5 planets visible to the naked eye. People have been watching it for thousands of years. Ancient Babylonian astronomers tracked its movements across the sky and built tables predicting where it would be years into the future. The Romans named it after Saturn, their god of agriculture and time. For most of human history, it was just a bright, slightly yellowish point of light wandering slowly against the fixed stars. Then, in 1610, Galileo Galilei pointed a telescope at it for the first time. What he saw confused him completely. He described Saturn as appearing to have 2 companion objects, one on either side. He thought he was looking at a triple planet. Then, a couple of years later, when he looked again, the companions had vanished. He was baffled. He wrote that Saturn had devoured its own children, a reference to the mythological figure because the strange objects had simply disappeared. What Galileo was actually seeing, though he didn't understand it, were Saturn's rings tilted edge-on to Earth. When the rings are aligned exactly edge-on from our vantage point, they almost disappear. The rings are so thin relative to their width that at the right angle they essentially vanish. The first person to correctly identify them as a flat ring system was Christian Huygens, a Dutch astronomer, in 1655. He also discovered Saturn's largest moon, Titan, in the same year. And in 1675, Giovanni Cassini discovered a gap in the ring system, the dark division that now bears his name, the Cassini division, and proposed that the rings weren't solid, but made up of many separate particles. He was right. But even then, even as astronomers began to understand what they were actually looking at, the sense of beauty dominated. The rings were a marvel. The planet was a jewel. Nobody was thinking about the terror hiding underneath. To start understanding what makes Saturn genuinely frightening, you have to understand what Saturn actually is. Saturn is a gas giant. It has no solid surface, no ground to stand on, no crust, no ocean floor, no rocky landing zone. If you were somehow transported to Saturn and released into its atmosphere, you wouldn't land. You would simply fall and keep falling, deeper and deeper into an atmosphere that gets thicker and hotter and more crushing with every passing second, until the pressure and heat became so extreme that the concept of falling would stop meaning anything at all. Saturn's diameter is roughly 74,000 miles. It is the second largest planet in the solar system, after Jupiter. You could fit about 760 Earths inside it by volume. 760. And yet, despite its enormous size, Saturn is the least dense planet in the solar system. In fact, it is the least dense object of any significant size in our entire solar system. Its average density is about 0.69 grams per cubic centimeter. Water has a density of 1 gram per cubic centimeter. This means that if you could find a bathtub large enough to hold a planet roughly 74,000 miles wide, Saturn would float in it. It would bob on the surface. That single fact is one of the strangest in all of planetary science. A planet almost 8 times the diameter of Earth, with a mass about 95 times greater than Earth's, would float on water. The reason for this is composition. Saturn is made overwhelmingly of hydrogen and helium, the two lightest elements in the universe. Hydrogen alone makes up about 96% of its mass. There is very little of anything else. No iron, no silicon, no dense rocky material in any quantity. It is, in essence, an enormous ball of the same stuff that makes up stars, just not quite massive enough to ignite fusion and become one. If Saturn were about 80 times more massive than it actually is, the pressure and temperature in its core would reach thresholds high enough to trigger hydrogen fusion. It would become a star. Instead, it sits in this strange in-between zone. Not quite a star, but not a rocky, solid world either. Something altogether different. And what happens inside that enormous ball of lightweight gas is where things start to get genuinely strange. The atmosphere of Saturn is where the first layer of terror lives. From space, Saturn looks smooth. Gentle bands of gold and cream and pale brown wrapping around it in wide stripes. It looks calm. It is not calm. Those bands are the visible tops of enormous atmospheric systems, jet streams and circulation patterns, driven by Saturn's internal heat and its rapid rotation. Saturn rotates once every 10 hours and 33 minutes. For a planet nearly 10 times the diameter of Earth, that is extraordinarily fast. Earth takes 24 hours to complete one rotation. Saturn does it in less than half that time. That rapid spin distorts the planet's shape. Saturn isn't a perfect sphere. It bulges noticeably at its equator and is flattened at its poles. The equatorial diameter is about 74,000 miles, but the polar diameter is only about 67,000 miles. The difference, around 7,000 miles, is visible even in amateur telescope images. Saturn is the most oblate, the most visibly squashed of all the planets in the solar system. But the spin doesn't just distort the shape, it drives the winds. And Saturn's winds are extraordinary. Near the equator, wind speeds have been measured at around 1,100 miles per hour. 1,100 miles per hour. Earth's most powerful hurricanes produce sustained winds of around 200 miles per hour. The most devastating tornadoes on record have been clocked at around 300 miles per hour. Saturn's equatorial jet stream is moving at more than 3 times the speed of those record-breaking tornadoes. And it doesn't stop. It doesn't weaken when it runs out of warm ocean water to feed it. It doesn't dissipate when it makes landfall. There is no landfall. The jet stream simply circles the planet endlessly at over 1,000 miles per hour, powered by Saturn's own internal heat, radiating outward from the deep interior. It has been doing this, without pause, for as long as Saturn has existed. 4.5 billion years of unbroken, relentless wind. To appreciate what that actually means, what a wind of 1,100 miles per hour actually does, Consider that the speed of sound in Earth's atmosphere at sea level is about 767 miles per hour. Saturn's equatorial jet stream is supersonic by Earth standards. A wind that would be moving faster than the crack of a rifle shot, faster than a military fighter jet at maximum thrust. And it wraps all the way around a planet with a circumference of 227,000 miles. Nothing slows it down. Nothing interrupts it. There is no coastline where it makes landfall and loses energy. There are no mountain ranges to deflect or break up the flow. It simply circulates, powered from below by the heat rising out of Saturn's interior, and it has been doing exactly that since the planet formed. Now consider what it would mean to fly an aircraft through this environment. A modern passenger jet has a cruising speed of around 550 miles per hour. If you put that aircraft into Saturn's equatorial jet stream, the wind alone would be moving at twice the aircraft's cruising speed. The aerodynamic forces on any structure entering that atmosphere at those speeds would be ferocious. There would be no stable flight. There would be no level cruising. There would only be the howling wall of wind and the crushing pressure building from below. Saturn's atmosphere is not a place, anything designed for flight. As we understand, flight could survive. It is a place where the wind is the primary physical fact, and everything else, chemistry, temperature, pressure, is secondary to the sheer kinetic violence of the atmospheric motion. But the winds are only the beginning, because within Saturn's atmosphere, storms form. And Saturn's storms are nothing like anything that happens on Earth. Every 20 to 30 years, something extraordinary happens on Saturn. A storm erupts at equatorial latitudes that grows so large, so quickly, and so dramatically that it becomes visible from Earth through a backyard telescope. These events are called great white spots. The historical record of their occurrences goes back to the 1900s, and astronomers believe they have been recurring on Saturn for far longer than that. They are predictable enough that when one doesn't appear roughly on schedule, astronomers take notice. The most recent and most studied one occurred in 2010 and 2011. In December of 2010, a bright white spot appeared in Saturn's northern hemisphere. Astronomers spotted it almost immediately and began watching. Within weeks, it had expanded into a band of storms that stretched completely around the planet. A storm system that girdled Saturn at its latitude like a belt, completely encircling a planet with a circumference of roughly 227,000 miles. The head of the storm, the most convectively active, churning part, was alone about 12,000 miles wide. A single storm, feature larger than Earth. NASA's Cassini spacecraft, which was in orbit around Saturn at the time, had a ringside view. What it recorded was extraordinary. The storm produced lightning bolts roughly 10,000 times more powerful than the most powerful lightning strikes on Earth. 10,000 times. The radio waves generated by that lightning could be detected from Earth. The storm churned Saturn's upper atmosphere so violently that it dragged material from deep layers upward, mixing the atmospheric chemistry in ways scientists were still working to fully understand years later. It persisted for roughly 200 days before eventually merging with its own turbulent wake and fading. 200 days of continuous, planet-girding storm. And then it was over. Until the next one, perhaps 20 or 30 years from now, when the cycle begins again. But the great white spots, as remarkable as they are, aren't the most permanent, or in some ways the most eerie feature in Saturn's atmosphere. For that, you need to look at the North Pole. When the Cassini spacecraft first sent back clear images of Saturn's North Pole, scientists expected to see something broadly familiar. A polar vortex, perhaps. Some kind of circular circulation pattern near the axis. What they saw instead left them genuinely puzzled. There, sitting at the top of Saturn's axis, was a massive hexagonal cloud pattern. A hexagon. 6 perfectly straight sides. Each side roughly 8,700 miles long. The entire structure is large enough to contain 2 Earths placed side by side. It had been there since at least the Voyager flybys of the early 1980s. That means this hexagonal storm system has been continuously present in Saturn's atmosphere for at least 4 decades of direct observation, and quite possibly much longer than that. The hexagon rotates. It completes one full rotation in about 10 hours and 39 minutes, which is close to Saturn's internal rotation rate, suggesting it's tied to something deep in the planet, rather than just being a superficial feature of the upper atmosphere. Inside the hexagon, the winds are immense. Speeds approaching 200 miles per hour, circling around a central vortex at the very pole. That central vortex, a massive churning cyclone at Saturn's North Pole, is itself about 50 times larger than a typical Atlantic hurricane on Earth. For a long time, scientists struggled to explain why it was a hexagon. Why not a circle, which is what you'd expect from a simple rotating vortex? The answer, worked out through laboratory experiments and computer modeling, involves the interaction between the fast-moving polar jet stream and slower air masses at slightly lower latitudes. Under exactly the right conditions, this interaction creates a standing wave, a wave pattern that stays fixed relative to the planet's rotation with 6 sides. 6 sides happens to be the stable solution for the particular combination of jet stream speed and planetary rotation rate that Saturn possesses. It's a fluid dynamics phenomenon. The hexagon is real, it's physical, it has been stable for decades, and it is one of the most alien-looking things in the solar system. The color of the hexagon has even changed over time. In the years when Cassini arrived, Saturn's northern hemisphere was in winter, and the polar hexagon appeared a deep blue color, Saturn's equivalent of a polar winter sky. As the northern hemisphere moved into summer during Cassini's mission, the color shifted toward golden, as photochemical reactions changed the chemistry of the atmosphere. A season on Saturn lasts about 7 Earth years, and the planet's atmosphere changes color with the seasons, just as leaves change color on Earth, though for very different reasons, driven by sunlight-driven chemistry in the clouds rather than the chlorophyll of trees. But to truly understand Saturn's capacity for extremity, you have to go deeper. Beneath the visible atmosphere, things escalate very quickly. Descending into Saturn is, in concept, a one-way journey. You enter through the cloud tops. The first cloud layer you'd encounter is made of ammonia ice crystals. These are the white and cream-colored clouds visible from Earth. Below that, the temperature rises, and you encounter clouds made of ammonium hydrosulfide, a compound that, on Earth, smells profoundly unpleasant. Below that, water ice clouds. And below that, liquid water droplets. But you're still in what we would call the atmosphere. The pressure is building with every mile of descent. On Earth, atmospheric pressure at sea level is 1 bar. That's what our bodies are adapted to. For every descent into Saturn's atmosphere, the pressure climbs relentlessly. A few hundred miles down, the pressure is already crushing. The gas around you grows denser, hotter, more opaque, And then, at some point, there is no longer a meaningful distinction between the atmosphere and the interior. The gas simply gets denser and denser without any boundary. There is no surface. No moment where gas ends and solid begins. It is a continuous, seamless transition from thin gas to something that no longer behaves like gas at all. At depths of several thousand miles, the pressure reaches levels around 2 million times Earth's atmospheric pressure. At those pressures, hydrogen doesn't behave the way we're used to. Hydrogen, at normal conditions, is a light, colorless, flammable gas. At extremely high pressures, it first transitions to a liquid. But squeeze it further, and Saturn's interior does exactly that, and something extraordinary happens. The electrons that normally stay bound to individual hydrogen atoms are forced free. They begin moving freely through the material, the way electrons move through a metal. The hydrogen becomes electrically conductive. It becomes, in the language of physics, metallic hydrogen. This is a state of matter that for most of human history was purely theoretical. We knew the pressures inside gas giants were high enough to produce it, but we couldn't create it in a laboratory. In recent decades, using extreme high-pressure equipment, scientists have managed to produce tiny samples of metallic hydrogen for fractions of a second. What they found matched theoretical predictions. Deep inside Saturn, there is a vast region, thousands of miles thick, where hydrogen exists as a metallic fluid. Not solid, not gas. A liquid metal made of the lightest element in the periodic table. This metallic hydrogen layer is almost certainly responsible for Saturn's powerful magnetic field. As it churns and flows in Saturn's deep interior, driven by convection currents and the planet's rapid rotation, it generates electrical currents. Those electrical currents generate a magnetic field. Saturn's magnetic field is roughly 578 times more powerful than Earth's. It extends far out into space, creating a magnetosphere, a region of space dominated by the planet's magnetic influence that stretches millions of miles from the planet. The interaction between the solar wind and Saturn's magnetosphere produces auroras near the poles, similar in concept to Earth's northern and southern lights, but far more energetic and on a vastly larger scale. These auroras are primarily ultraviolet and infrared in wavelength, outside the range of human vision. But Hubble's Space Telescope observations have captured them. They form rings around Saturn's poles, bright curtains of emission marking where charged particles from the magnetosphere funnel down into the atmosphere and collide with atmospheric gases. Saturn's poles glow, constantly, invisibly to the naked eye, but real. At the very center of Saturn, there is almost certainly a core. Models suggest it's somewhere between 10 and 20 times Earth's mass, composed of rock, metal, and possibly ice, compressed to extraordinary densities. But even this inner core is not fully understood. Some recent models, informed by measurements of how Saturn's gravity field oscillates, a technique called seismology applied to a planet, suggest that the core may not be a sharp, distinct ball at all. It may be what's called a fuzzy core, a diffuse region where rocky material is dissolved and mixed into the metallic hydrogen surrounding it. The core bleeds into the interior above it, without a clear edge, a planet that blurs, all the way down, from cloud top to center. No boundaries, no surfaces, just gradual, relentless compression. If the interior of Saturn is terrifying in its extremity, the rings are terrifying in a completely different way. They are one of the most beautiful things in the solar system. They are also one of the most violent and one of the most temporary. The rings of Saturn span an enormous distance. From the inner edge of the D ring, the innermost and faintest ring, to the outer edge of the A ring, the main visible ring system extends roughly 170,000 miles from the planet. If you placed that ring system at Earth, it would more than span the distance from Earth to the Moon. And yet, for all their breadth, the main rings are extraordinarily thin. On average, their thickness is somewhere between 30 feet and about 3,000 feet. That ratio, 170,000 miles wide, a few hundred feet thick, is more extreme than the ratio of a sheet of paper to a football field. The rings are made mostly of water ice, particles ranging from tiny grains of dust to chunks the size of a house, all orbiting Saturn in a flat disk. That sounds tranquil. It isn't. Within the rings, collisions happen constantly. Every particle is in its own orbit. Orbits at slightly different distances from Saturn travel at slightly different speeds. Particles jostle and collide continuously, shattering into smaller pieces, occasionally clumping together. The rings are in a constant state of grinding, churning, slow-motion catastrophe. Some of the more dramatic effects come from the interaction between the rings and Saturn's moons. Saturn has 85 confirmed moons, more than any other planet in the solar system. Several orbit within or just outside the rings, and their gravitational influence shapes the rings in ways that took decades to understand. The moon Prometheus, for example, orbits just inside the narrow F ring. Every time Prometheus makes a close pass to the F ring, it gravitationally tugs on the ring material, creating channels and kinks and clumps in the ring. It leaves its gravitational fingerprint in the ring structure on every single pass. Watch the F ring over time, and you can see the distortions Prometheus leaves behind, wave after wave, each one an imprint of a moon's gravity. Then there are the resonances. When a moon's orbital period is a simple fraction, 1/2, 1/3, 2/3 of a ring particle's orbital period, the moon exerts a regular, repeated gravitational nudge on those particles at the same point in their orbit. These nudges add up over time. They can push particles into new orbits or clear them out of certain regions entirely. This is how the Cassini division is maintained. That gap in the rings, about 2,900 miles wide, corresponds to a 2-to-1 resonance with Saturn's moon, Mimas. A particle orbiting in the Cassini division would go around Saturn exactly twice for every one orbit of Mimas. That repeated gravitational nudge, always at the same point in the particle's orbit, has cleared out most of the material in that zone over millions of years. The Cassini division looks empty from Earth. It isn't quite empty. There are still some particles there, but it's dramatically less dense than the rings on either side. Mimas carved it. But the moons don't just shape the rings. They also feed them and drain them. Saturn's rings are actively losing material. Charged particles from the rings are continuously funneled along Saturn's magnetic field lines into the upper atmosphere in a process called ring rain. Researchers using data from the Cassini spacecraft estimated that Saturn is losing somewhere between 400 and 900 kilograms of ring material per second. Not per year, per second. At that rate, the entire ring system, which has an estimated mass roughly equal to the mass of the moon Mimas, about 40 quintillion kilograms, would be gone in somewhere between 40 million and a few 100 million years. In cosmic terms, that is a blink. The solar system is 4.5 billion years old. If the rings have been eroding at their current rate, they've only existed in their current spectacular form for a very short time, geologically speaking. Some estimates put the age of the main ring system at only around 100 million years. That would mean the rings of Saturn are geologically young. They didn't form with the planet. They formed, or at least took their current form, far more recently. The rings that Galileo puzzled over, the rings that have become perhaps the most iconic image associated with any planet in the solar system, may be a temporary phenomenon on the timescale of solar system history. This is what makes Saturn's rings genuinely unsettling once you understand them. Not just their violence, but their impermanence. We happen to exist at a moment when Saturn wears its most spectacular adornment. That moment will not last. Future civilizations looking at Saturn hundreds of millions of years from now may see a very different planet. The rings will be gone, or reduced to a faint shadow of what they are today. And new civilizations, if they arise on some future world orbiting some distant star, may look at our solar system and see a Saturn that looks nothing like the Saturn we know. A plain, banded gas giant, without the crown. The question of where the rings came from is still not fully resolved. But the leading idea is that they represent the shattered remains of something that once existed, something substantial, possibly a moon that wandered too close to Saturn. Within a certain distance from Saturn, called the Roche limit, the tidal forces become strong enough to overwhelm the gravitational cohesion of a solid body. A moon crossing inside the Roche limit would begin to break apart. Tidal forces pulling harder on the near side than the far side would stretch and tear the object apart, shredding it into smaller and smaller pieces until nothing was left but a disk of debris. That debris, over millions of years, would spread and collide and grind and sort itself into the flat, ring-like structures we see today. Some models suggest this destruction happened relatively recently. In geological terms, perhaps around the time of the late heavy bombardment, when the solar system was experiencing a period of intense gravitational upheaval that sent many objects on new trajectories. A moon at the wrong place at the wrong time, drawn inside the Roche limit by some gravitational interaction, shredded by Saturn's tides, and turned into a ring. It's a violent origin story for something so beautiful. But Saturn has a habit of making beautiful things through violent processes. One of the most telling lines of evidence for the rings being relatively young comes from their composition. The ring particles are extraordinarily bright and reflective. The main rings reflect about 60 to 80% of the sunlight that hits them. This high reflectivity is consistent with the rings being made mostly of very pure water ice. But here's the issue. Space is not clean. The solar system is full of dust, interplanetary dust, debris from comets and asteroids, dark material constantly drifting through the solar system. Over time, this dust coats everything. Older surfaces darken. The moon's surface is dark in many places because it has been sitting in the solar system, accumulating space dust for over 4 billion years. If Saturn's rings were also 4.5 billion years old, they should look dark. They should be contaminated, coated in a layer of infall material, far less reflective than they currently are. The fact that they are still so bright and so pure in composition suggests they haven't been around long enough to get dirty. They're too clean to be ancient. The inner moons of Saturn, the ones that orbit close to the planet and within or near the rings, also give clues about the ring's youth. These moons are thought to have formed from ring material over relatively short timescales. If the rings are young, The inner moons are young too. Pan, Atlas, Prometheus, Pandora, Epimetheus, Janus. All of these small, irregularly shaped moons, orbiting within or just outside the main rings, are, in this model, not ancient bodies left over from the formation of the solar system. They are new. They assembled themselves from ring particles, relatively recently, in geological terms, and they are continuing to grow or to change as ring material continues to collide with them, coat them, alter their shapes. This is a solar system actively changing, right now, not in some abstract future. The rings are eroding. The inner moons are being shaped by ring material, accumulating on them. The planet below is receiving a continuous rain of ring particles. The system is in motion. It will not look the same in 100 million years as it does today. And it didn't look the same 100 million years ago as it does now. The Saturn we know is a snapshot of an ongoing process. A moment caught in a very long, very slow transformation. There is something particularly interesting about how the moons of Saturn interact with each other, not just with the rings. Saturn's moon system contains some of the most complex gravitational interactions in the solar system. Several of Saturn's moons are locked in what are called orbital resonances with each other. Enceladus and Dione, for example, are in a 2-to-1 resonance. Enceladus completes exactly 2 orbits for every 1 orbit of Dione. This means that every time Enceladus laps Dione, it is at the same point in both their orbits. The gravitational interaction between them is therefore periodic and amplified, the same configuration recurring over and over. This resonance is not just a coincidence. It has been maintained because the resonance is stable, and because the small nudges that would otherwise push Enceladus and Dione out of the resonance are counteracted by the resonance itself. More importantly, this resonance has a physical consequence for Enceladus. The repeated gravitational nudge from Dione deforms Enceladus as it orbits, squeezing and stretching it slightly with every orbital cycle. This is tidal heating, the same principle that heats a piece of metal if you bend it repeatedly. Friction within Enceladus's interior, generated by the tidal deformation, produces heat. That heat is almost certainly what maintains the liquid water ocean beneath Enceladus's ice shell. Without the resonance with Dione, Enceladus might be a frozen, geologically inactive world. Instead, it is one of the most geologically active bodies in the solar system, venting its ocean into space, possibly harboring life. The orbital dance between 2 moons, hundreds of thousands of miles apart, is what creates the conditions for a potentially habitable ocean world. Gravity connects everything. Titan's orbit also affects other moons in Saturn's system. Titan is so massive it contains more than 90% of the mass of all Saturn's moons combined that it dominates the dynamics of the outer part of the moon system. Several of the smaller moons in the outer system follow complex, chaotic orbits that have been shaped over billions of years by gravitational interactions with Titan. Some of these small outer moons, sometimes called the Norse group, the Inuit group, and the Gallic group, are thought to be captured objects, asteroids or Kuiper belt, objects that wandered too close to Saturn and were captured into orbit. They orbit Saturn in retrograde opposite to the direction of the planet's rotation, which is a signature of captured rather than formed-in-place objects. Saturn has been catching things. Over billions of years, it has swept up small bodies that came near enough to be captured, adding them to its growing collection of moons. The Saturn system we see today is not just what formed there. It is also what Saturn has collected along the way. An accumulation. A record of 4.5 billion years of gravitational history. The question of whether life exists in the outer solar system is one that Saturn's system has made genuinely urgent. Before the Voyager missions, the assumption was that life in the solar system, if it existed beyond Earth at all, was confined to the inner solar system. To Mars, perhaps. To conditions where sunlight was strong enough to warm a surface, to drive photosynthesis, to maintain a temperate climate. Liquid water was thought to require proximity to the sun. That assumption dissolved the moment scientists saw Enceladus. And before Enceladus, it dissolved for Jupiter's moon Europa, which appears to have a similar subsurface ocean. The discovery that liquid water can exist far from the sun, kept liquid, not by sunlight, but by the tidal heating from orbital resonances, fundamentally expanded the range of places we now have to look for life. The outer solar system is not a frozen wasteland where nothing interesting can happen. It is a collection of worlds with hidden oceans, with organic chemistry, with energy sources that have nothing to do with the sun. And in Saturn's system specifically, there are at least two worlds, Enceladus and Titan, where the ingredients for life as we know it, or life as we might imagine it, appear to be present. This changes everything about how we think about the likelihood of life in the universe. Because if life can arise in the cold outer reaches of a solar system, on a tiny moon in orbit around a gas giant, with only tidal heating and chemical energy to work with, then the number of habitable environments in the galaxy is vastly larger than we once thought. Every star in the Milky Way, with a Jupiter or Saturn analog, could, in principle, have moons with subsurface oceans. Every outer moon in a tidal resonance is a potential habitat. There are hundreds of billions of stars in the Milky Way. The outer solar system scenarios that Saturn's moons are teaching us about could be playing out on an enormous number of worlds we can't even see yet. Saturn is not just a planet. It is a proof of concept. It is showing us that the universe is more habitable than we imagined. And it is doing so from nearly 1 billion miles away, through the thin radio signals that make it back to Earth from a handful of spacecraft that humanity had the ambition and the skill to send there. Before the Cassini mission, we had images of Saturn's moons from the Voyager flybys, detailed photographs, but brief snapshots in time. Cassini gave us something different. 13 years in orbit. Over 4,000 orbits completed. Close flybys of dozens of moons. And what it found changed our understanding of what moons can be. Titan is Saturn's largest moon and, by any measure, one of the most extraordinary objects in the solar system. It is the second largest moon in the solar system, just barely smaller than Jupiter's Ganymede. It is larger than the planet Mercury, and it has something almost no other moon has: a thick atmosphere. Titan's atmosphere is about 1.5 times as dense as Earth's at the surface. It is made mostly of nitrogen, with methane and other organic compounds. The orange haze that gives Titan its distinctive color comes from complex organic molecules called tholins, formed when sunlight breaks apart methane and nitrogen molecules high in the atmosphere, and the fragments recombine into larger, more complex structures. These tholins rain down onto Titan's surface, coating it in a thin layer of complex organic material. On Titan's surface, the temperature is about -290 degrees Fahrenheit, or -179 degrees Celsius, cold enough that water ice is as hard as granite. But methane at those temperatures can exist as a liquid, and Titan has a methane cycle. The same way Earth has a water cycle: evaporation, clouds, rain, rivers, lakes, seas. Titan has one built on methane. There are lakes and seas on Titan's surface, filled with liquid methane and ethane. There are rivers that have carved channels through the landscape. There are dunes of organic material, dark sand dunes covering vast regions near the equator. When the Huygens probe released by Cassini descended through Titan's atmosphere in January of 2005, it sent back images during the descent and from the surface. The landscape looked, in some disorienting way, familiar. Rounded pebbles scattered across a flat plain. What appeared to be a shoreline, with drainage channels cutting through darker highland material. It looked like something you might see on Earth from a low-flying aircraft. But everything was alien. The rocks were water ice. The drainage channels were carved by methane, not water. The pebbles were smoothed, not by a flowing river of water, but by flowing liquid natural gas. Titan raises a question that is genuinely difficult to dismiss. If complex organic chemistry is happening there, if there is a liquid solvent, if there is energy from Saturn's tidal heating and from the faint sunlight that reaches that far out, is there life? Not life like ours. Not life based on water and the biochemistry we know, but perhaps a form of chemistry complex enough to develop self-replicating molecules. Something that uses liquid methane as its solvent, the way our cells use water. The honest answer is that we don't know. But the question is scientifically legitimate. Titan is, in many respects, a natural laboratory for prebiotic chemistry. A world where complex organic molecules are being synthesized continuously from simple raw materials, raining out of the sky, accumulating on the surface, dissolving in methane lakes. Something is happening there. The tholins on Titan's surface are some of the most complex organic molecules found anywhere in the solar system outside of Earth. Laboratory experiments that simulate Titan's atmospheric chemistry produce hundreds of different organic compounds, including amino acid precursors, molecules that, on Earth, are the building blocks of proteins. Those compounds are being made in Titan's atmosphere right now, every day, in enormous quantities. They drift down and accumulate on the surface. They dissolve into the methane lakes and seas. They interact with each other, with the methane, with the water ice in the bedrock beneath. Whether any of this chemistry crosses a threshold into something we would call life is unknown. But the direction it's heading from simple molecules toward increasing complexity is the same direction Earth's chemistry was heading 4 billion years ago. Saturn's largest moon may be running a slow version of the same experiment that produced life on Earth, running it on a different timeline, with different raw materials. At temperatures 290 degrees lower than anything life on Earth can survive. Whether it is a successful experiment is one of the most important questions science will attempt to answer over the next century. And we are going there to find out. Dragonfly will fly through Titan's atmosphere. It will land in different environments. It will sample the chemistry of the dunes, the lake shores, the crater floors, places where water ice and organic material have mixed at some point in geological history, creating exactly the kind of chemical complexity that might nurture life. If there is life on Titan, Dragonfly may detect it. If there isn't, Dragonfly will tell us where the chemistry stopped and why. Either answer will be extraordinary. Something is happening there. The Saturn system is so rich with potential that it is difficult to fully take in. It has 85 confirmed moons. It has a ring system that functions as a natural seismograph for the planet's interior. It has a magnetosphere that shelters its inner moons from the solar wind. It has a hexagonal polar storm that has been stable for at least 40 years. It has a core that may not have a boundary. It is losing its rings at a measurable rate every second, and hiding beneath the ice of at least one small moon, an ocean of liquid water that vents its contents directly into space. Every time a new instrument looks at this system more carefully, it finds something new. Every time a new model is built to explain what we observe, it has to account for another layer of complexity. Saturn is not a simple system. It is one of the most dynamically rich, scientifically productive, and physically extreme environments in the solar system. And we have only begun to understand it. Then there is Enceladus. Enceladus is small, only about 313 miles in diameter, tiny by the standards of moons. And yet, Enceladus may be the single most exciting body in the solar system when it comes to the question of life beyond Earth. In 2005, Cassini flew close to Enceladus and detected something unexpected: water vapor and ice particles erupting from the South Polar region in enormous plumes. Geysers. Jets of material erupting from a series of long, parallel fractures in the ice near the South Pole. Fractures that, because of their distinctive appearance in infrared images, were nicknamed tiger stripes. Each stripe is roughly 80 miles long, and from these stripes, water vapor, ice particles, organic molecules, and molecular hydrogen are being continuously blasted into space at around 1,000 miles per hour. This material forms a vast plume that extends hundreds of miles above the surface and spreads into space. Cassini flew through it, directly through the plume, multiple times. What it found shocked the scientific community. The plume contains complex organic compounds. It contains silica nanoparticles, tiny particles of rock material, which can only form when liquid water at high temperatures is in direct contact with silicate rock. That means somewhere beneath Enceladus's ice shell, there is a liquid water ocean. And at the bottom of that ocean, where the water meets the rocky interior, there are hydrothermal vents. On Earth, hydrothermal vents at the bottom of the ocean, where hot, mineral-rich water gushes from cracks in the seafloor, support entire ecosystems. Life that has never seen sunlight. Life that gets its energy entirely from chemical reactions involving the minerals and gases from the vents. Microbes, worms, crabs, fish, all living in permanent darkness, sustained entirely by the heat and chemistry below them. Enceladus appears to have exactly those conditions. Liquid water, a rocky seafloor, hydrothermal activity, organic molecules, molecular hydrogen, which is a chemical energy source that certain microbes on Earth use to power their metabolism. Everything we associate with habitability for the kind of life we know. And because Enceladus is actively venting material from its ocean into space, we wouldn't even need to land and drill through the ice to sample it. We could fly through the plume and collect the ocean water directly. Cassini did this. A future mission carrying more sophisticated life detection instruments could, in principle, detect biosignatures in the plume simply by flying through it. Of all the places in the solar system where life might exist beyond Earth, Enceladus is among the strongest candidates. A tiny moon, in orbit around an enormous gas giant, nearly 900 million miles from the Sun, quietly venting its hidden ocean into space like a message written in water vapor. a message we have already partially read. The organic molecules, Cassini, found in the plume. The silica particles, indicating hydrothermal activity. The molecular hydrogen, indicating ongoing geochemical reactions. These are not ambiguous signals. They are clear indicators of the conditions we associate with habitability. Whether those conditions have produced life or are in the process of doing so remains the open question. But it is no longer a question about whether the conditions are right. They are right. The question is whether life has taken advantage of them. And that is a question that only a return mission can answer. The story of how we know all this is its own kind of remarkable. In 1977, NASA launched two spacecraft, Voyager 1 and Voyager 2. They were sent on a grand tour of the outer solar system, taking advantage of a rare alignment of the outer planets that occurs roughly once every 175 years. This alignment, called the Grand Tour Trajectory, allowed a spacecraft to use the gravity of each outer planet to slingshot to the next one, visiting Jupiter, Saturn, Uranus, and Neptune in sequence, without needing enough fuel to reach each planet independently. The window for this trajectory was narrow. It would not come again for well over a century. The decision to send spacecraft on this trajectory was made in the early 1970s, and the engineering required to do it was extraordinary. The spacecraft had to be designed to operate for years, in the extreme cold and radiation of the outer solar system, billions of miles from Earth. They had to be capable of communicating from those distances on radio signals too faint for most receivers to detect. They had to navigate with a precision that seems almost impossible by the standards of the technology available in the 1970s. And they had to do all of this with computers that, by modern standards, had barely any capability at all. Voyager 1 reached Saturn in November of 1980. Voyager 2 followed in August of 1981. The images they sent back transformed our understanding of the planet. We saw for the first time the fine structure of the rings, the thousands of individual ringlets, the gaps, the waves, and braided patterns in the F-ring. We saw Titan's orange haze and got our first real sense of how thick its atmosphere was. We saw Enceladus's bright, almost mirror-like surface, so reflective that it suggested a young, geologically active world. We saw the cratered faces of Mimas, Dione, Rhea, Tethys. And we saw Saturn itself, up close, for the first time, the banded cloud tops, the enormous scale, the rings in 3 dimensions. The Voyagers gave us Saturn as a real place. Not just a point of light, not just a disk in a telescope, a world. But they were brief encounters. Voyager 1 spent only a few days in the Saturn system before being flung on its way toward interstellar space. What scientists really wanted was a spacecraft that would stay. That spacecraft was Cassini. Cassini launched in October of 1997 and arrived at Saturn in July of 2004 after a nearly 7-year journey of just over 2 billion miles. To get there, it used gravity, assists carefully planned flybys of Venus twice, then Earth, then Jupiter, each one using the planet's gravitational field to slingshot the spacecraft faster and farther toward the outer solar system. On arrival, Cassini had to perform one of the most precise maneuvers in the history of space exploration. To enter Saturn's orbit, it had to slow down dramatically. It fired its main engine for 96 minutes. One engine firing. One chance. Because of the distance from Earth, there was no possibility of real-time control. The signal to Saturn takes over an hour to arrive. By the time mission controllers could know if something had gone wrong, the maneuver was already long finished. Cassini had to do it alone, following pre-programmed instructions, while the team on Earth waited. And waited. The tension in mission control during those 96 minutes is difficult to overstate. Everything depended on that single burn. If the engine fired for slightly too long, Cassini would slow too much and fall into Saturn. If it fired for too short a time, the spacecraft would escape Saturn's gravity and fly off into deep space. And 13 years of mission planning would be gone. It worked. And what followed was 13 years of extraordinary science. Cassini discovered the geysers of Enceladus. It mapped Titan's surface in detail through its radar instruments, piercing the opaque orange haze and revealing lakes, seas, dunes, and mountains beneath. It found new moons. It discovered that the rings are far more dynamic and complex than anyone had understood. It measured the mass of the rings by tracking how the spacecraft wobbled in Saturn's gravity as it passed close to the ring plane. It found that the rings are making it rain, water ions funneling down from the rings along Saturn's magnetic field lines into the upper atmosphere. It measured the length of Saturn's day more precisely than ever before, a surprisingly difficult problem, because Saturn has no solid surface feature to track as a reference point. Saturn's radio emissions, which rotate with the deep interior and had been used as a proxy for the rotation period, turned out to vary. Different latitudes of the atmosphere rotate at different speeds. The rotation of the deep interior, the thing you'd actually want to measure to get the true day length, had to be inferred from subtle gravitational measurements. Cassini's gravity science team, using the spacecraft's precise orbital tracking, determined that Saturn's interior rotates in about 10 hours, 33 minutes, and 38 seconds. A number accurate to within seconds, determined by tracking the tiny gravitational wobbles of a spacecraft in orbit around a planet 886 million miles from Earth. It also discovered that Saturn's rings are geologically young. The composition, brightness, and rate of accumulation of dark material all pointed to a ring system no more than a few 100 million years old. This was not what most scientists expected. The expectation had been that the rings were ancient relics of the early solar system. Cassini showed that the rings are younger than the dinosaurs, a discovery that forced a fundamental rethinking of how the ring system formed and what it means for the evolution of Saturn as a planetary system. Then, in 2016 and 2017, NASA decided to use Cassini's remaining fuel for what they called the grand finale. It was a sequence of extraordinary orbits. In the first phase, Cassini flew in orbits that took it close to the outer F-ring. In the second phase, it began a series of dives through the gap between the inner edge of the rings and the top of Saturn's atmosphere. A gap about 1,500 miles wide. No spacecraft had ever gone there. Nobody knew for certain what Cassini would find. Would the gap be full of dust and debris that could damage the spacecraft? Would ring particles be raining down into the atmosphere in concentrations high enough to pose a risk? Nobody knew. On the first dive, mission controllers used Cassini's dish antenna as a shield, pointing it forward to protect the spacecraft's instruments in case the gap was full of hazardous material. The team held their breath. Cassini flew through and survived. And what it found was remarkable. The gap between the rings and the planet turned out to be relatively clear, but not empty. Cassini detected ring material falling into the atmosphere. Complex organic molecules including benzene, propene, and other hydrocarbons being pulled down from the rings into Saturn's upper atmosphere. The chemistry in that gap between the rings and the planet was far more complex than anyone had expected. Cassini also measured Saturn's magnetic field at closer range than ever before, and found that the field is almost perfectly aligned with the planet's rotation axis, more closely aligned than any other planetary magnetic field in the solar system. This is strange. For a magnetic field to be generated in the way Saturn's is believed to be generated, through the dynamo action of moving, conducting fluid, there needs to be some asymmetry. A perfectly aligned field shouldn't work by current theories. Saturn's field, being so precisely aligned, is a puzzle that planetary scientists are still working to resolve. One hypothesis is that there is a layer of stable, stratified fluid sitting above the metallic hydrogen dynamo region, acting like a filter that screens out the asymmetric components of the magnetic field before they reach the surface. Only the symmetric part gets through. If this is correct, Saturn's interior has a structure that is hiding the true complexity of its magnetic field generation from us. The surface we observe is a filtered, simplified version of the real thing happening deep below. After 22 grand finale dives, Cassini performed its final maneuver. On September 15th of 2017, it was deliberately guided into Saturn's atmosphere. The reason was planetary protection. After 13 years in the Saturn system, Cassini was running low on fuel. Without precise control, there was a risk it could eventually drift and collide with one of Saturn's moons, potentially contaminating Enceladus or Titan with microbes from Earth. To prevent that possibility, the decision was made to end the mission deliberately. Cassini entered Saturn's atmosphere at around 70,000 miles per hour. For about 90 seconds, it fired its thrusters to hold its antenna pointed toward Earth, transmitting data for as long as it possibly could. Then, the atmosphere overwhelmed it. It tumbled. The friction began tearing it apart. Within seconds, it was gone. The last signal took 83 minutes to reach Earth. When the signal stopped, the control room at the Jet Propulsion Laboratory went quiet. Members of the mission team, who had spent decades on the project, wept. 13 years of science. 133 gigabytes of data returned. Hundreds of scientific papers published. Dozens of moons discovered or confirmed. And at the end, the spacecraft fell into the planet it had spent 13 years studying. It became part of Saturn. In some sense, Cassini is still there, dissolved into Saturn's atmosphere, compressed, falling deeper. What Cassini left behind is not just data. It left behind questions about Enceladus and whether life survives in its hidden ocean, about Titan and the chemistry happening in its methane lakes and on its organic dusted shores, about the age and origin of the rings and what object was destroyed to create them, about the deep interior of Saturn and the exact nature of the fuzzy core, about the hexagonal polar vortex and what it tells us about atmospheric physics more broadly. These are not rhetorical questions. They are active areas of research. And some of them will have answers within our lifetimes. NASA is developing a mission called Dragonfly. Dragonfly is a rotorcraft lander, essentially a large, nuclear-powered drone designed to fly through Titan's atmosphere and land at multiple sites across the surface, studying the chemistry at each one. It will investigate the kinds of organic molecules present and how they interact with the environment. Dragonfly is currently planned for launch in the 2030s. Scientists and engineers are also developing concepts for a dedicated Enceladus mission, an orbiter and plume sampler that would return to that tiny, extraordinary moon and spend years analyzing its ocean-vented material with instruments far more sophisticated than anything Cassini carried. The detection limits for amino acids, for cell membranes, for biosignatures of any kind would be orders of magnitude better than what was available in 2005 when Cassini made its first plume flyby. The next chapter of Saturn science is coming. Whatever flies next will take years to arrive. The distance is immense. The journey is long. But the questions are too important to leave unanswered. There is one more aspect of Saturn that deserves attention, not its storms, or its rings, or its extraordinary moons, or its metallic interior, but what it has done for the rest of us, for Earth. Saturn, along with Jupiter, has played a protective role in the solar system's history. The outer solar system, in the early period of solar system formation, was a much more violent place than it is today. There were far more comets and asteroids on chaotic, highly elliptical orbits, trajectories that brought them through the inner solar system on a regular basis. The early Earth was bombarded heavily. This period, called the Late Heavy Bombardment, lasted until roughly 3.8 billion years ago and significantly shaped the early conditions on Earth and the other inner planets. Over billions of years, following that period, the gravitational influence of Jupiter and Saturn helped clear out and stabilize the solar system. The two gas giants act as gravitational vacuum cleaners. Their enormous mass means that small bodies passing near them are either captured into stable orbits, flung out of the solar system entirely, or directed into the Sun. Without Jupiter and Saturn maintaining this gravitational influence across billions of years, the rate of large impacts on Earth would likely be significantly higher than it has been. Some researchers argue that the existence of large gas giant planets in appropriate orbits may be a requirement for the long-term stability of a planetary system hospitable to complex life. A planet like Earth, orbiting in the habitable zone of a star, might need a Saturn in the outer system to help keep the neighborhood stable enough for life to develop without being catastrophically interrupted every few million years. This idea is debated. Other researchers argue the relationship is more complicated and that the gas giants have also sent objects toward the inner solar system at various points in history, not just away from it. The truth is almost certainly nuanced, but the connection is real. Saturn is not just a distant spectacle. Its gravity has shaped the history of our own planet. It is part of the story of Earth, part of the story of us. There is also the story of Saturn's internal heat source. This is something not widely discussed, but it's one of the more remarkable things about the planet. Saturn radiates more energy than it receives from the Sun, roughly 2.5 times more. That means Saturn has an internal heat source, something generating energy deep inside the planet, and that energy flows outward, driving the atmospheric circulation, powering the winds, fueling the storms. What is it? The leading hypothesis involves a process called helium rain. In Saturn's interior, there is a region where the temperature and pressure are such that helium, which has been mixing uniformly with hydrogen throughout the planet since its formation begins to condense into droplets. Similar to the way water droplets form in a cloud, but happening deep inside a planet. These helium droplets are slightly denser than the surrounding hydrogen, so they fall. They rain downward, toward the deeper interior. As they fall, they release gravitational potential energy. That released energy is converted to heat. It is a slow, continuous, gravitational drizzle happening inside Saturn right now, at this very moment. Invisible, inaudible, but real. Helium droplets falling through liquid metallic hydrogen in the crushing dark interior of a gas giant, quietly warming the planet from within. This process also explains why Saturn's atmosphere is depleted in helium compared to Jupiter's. Jupiter is larger, hotter internally, and the helium rain process hasn't proceeded as far. Saturn, being smaller and somewhat cooler in its upper interior layers, has been raining helium for longer, and more of it has settled to the deep interior over billions of years. The energy released by this helium rain drives everything above it. The 1,100 miles per hour equatorial winds. The planet-girdling storms that recur every few decades. The hexagonal polar vortex that has been stable for as long as we've been able to see it. All of it ultimately powered by a slow, invisible rain of condensing helium falling through a sea of metallic hydrogen. A rain that no instrument has ever directly observed. A rain inferred entirely from measurements of the planet's heat output and atmospheric composition. Saturn's interior hides it, but the evidence is written in everything above. Now, consider what all of this means when you put it together. Saturn is a planet nearly 10 times the diameter of Earth. It has no solid surface. If you descended into it, you would fall indefinitely through layers of cloud and ammonia, ice and liquid hydrogen, through a transition to metallic hydrogen conducting electricity like a wire toward a core that may not have a clear boundary at all. Its winds blow at over 1,000 miles per hour and have done so without interruption for 4.5 billion years. Its storms, when they occur, encircle the entire planet. Its North Pole contains a hexagonal atmospheric structure larger than 2 Earths, stable for decades. Driven by dynamics that can be reproduced in laboratory tanks but still hold open questions at planetary scales. Its rings, the most recognizable feature of any planet in the solar system, are geologically young, constantly eroding, and will eventually disappear entirely. They are made of colliding, grinding ice particles in a structure so thin relative to its width that it defies easy comprehension. It has 85 confirmed moons. Among them is Titan, a world with a thick atmosphere, liquid methane seas, and chemistry that might have crossed the threshold into something like life. And Enceladus, a tiny world with a hidden ocean venting its contents into space, containing every ingredient we associate with life as we know it. Its interior contains metallic hydrogen, a state of matter so extreme it was theoretical until recently. Its magnetic field is enormous and nearly perfectly aligned, which by current models it shouldn't be. It is heated from within by helium rain. Its rings are tilting the planet itself through gravitational resonance with Neptune. It has contributed to the stability of the inner solar system and the conditions that allowed life to emerge on Earth. All of this is Saturn, the same planet that looks, from a distance, like a golden disk with a halo of ice. The same planet that made Galileo think he was seeing a triple star. The same planet that people have used to name a day of the week Saturday is Saturn's day for over 2,000 years, without understanding anything about what it actually is. To stand back and look at Saturn from a true distance from the outside, the way you see it in telescope images, is to see one of the most visually arresting things the solar system produces. That golden disk, banded and oblate. Those rings, sweeping out in a nearly perfect flat plane, bright on the sunward side, shadowed on the other. The faint dots of moons strung out along the ring plane like beads on a wire. It looks like something that was designed. Like a diagram of an idealized planet, drawn by someone who wanted to make absolutely sure you knew you were looking at something extraordinary. But Saturn wasn't designed. It formed out of a collapsing cloud of gas and dust 4.5 billion years ago. The same process that formed the Sun, that formed Earth, that formed every object in this solar system. What it became is a product of physics. Gravity pulling material together. Angular momentum preserving rotation. Composition determining density. Mass determining the conditions of the interior. Orbital dynamics shaping the ring system over millions of years. Every feature of Saturn, the winds, the hexagon, the metallic hydrogen, the rings, the diversity of its moons is the result of the same fundamental physical laws operating on the same raw materials that built everything else. There is no special ingredient, no exception to the rules. And yet, the result is Saturn. The result is the most complex planetary system in our solar system outside of Jupiter. A system that has surprised every mission we've sent to it. A system that is actively changing, losing material, gaining new understanding, and producing new questions faster than we can answer the old ones. A planet that floats on water but has hurricanes that would dwarf continents. A planet that has a storm shaped like a hexagon sitting at its north pole that has been running for at least 40 years. A planet whose interior is made of liquid metal derived from the most abundant element in the universe. A planet whose rings are simultaneously iconic and temporary, beautiful and violent, younger in their current form than the dinosaurs were on Earth. A planet whose moons include one world with liquid methane seas and complex organic chemistry, and another tiny world whose hidden ocean vents its contents directly into space. A planet that has helped protect Earth from catastrophe over billions of years. A planet that absorbed the spacecraft we sent to study it. Saturn is not scary in the way a horror film is scary. It is not malicious. It has no intent. It doesn't know we exist. It is scary the way the ocean at night is scary. The way a mountain face is scary. The way a lightning bolt striking 100 feet away is scary. It is the fear that comes from encountering something vast, powerful, indifferent, and real. Something that operates on scales and by rules that make our ordinary experience feel small and provisional. Something that was here long before us and will be here changing slowly, losing its rings, reshaping its moons, raining helium into its own interior long after we are gone. And in the end, that indifference is what makes it most frightening of all. Saturn does not care about us. It doesn't need to. It simply exists. An ancient, enormous, still churning engine of physics wrapped in a temporary ring of ice hanging in the outer dark, waiting not with intent or patience, but just by existing for the next person to point a telescope at it and feel, even for a moment, the weight of how small they are. There are layers to Saturn that most people never hear about. And every one of them adds to the picture of a planet that is, on closer inspection, stranger and more extreme than almost anything else orbiting the Sun. Take Mimas. Mimas is one of Saturn's inner moons. It orbits at a distance of about 115,000 miles from Saturn's center, closer to Saturn than any of the other major moons. It is small, roughly 250 miles across, and it has a feature that makes it instantly recognizable. On one hemisphere, there is an impact crater roughly 88 miles in diameter, almost a third the width of the Moon itself. The crater is named Herschel, after William Herschel, who discovered Mimas in 1789. The crater is so large, relative to Mimas, that whatever impacted it came close to shattering the Moon entirely. The impact that created Herschel crater must have been one of the most violent events in Mimas's history. The shockwave from the impact ran through the entire Moon. On the opposite side of Mimas from the crater, there are strange grooves and fractures in the surface that are thought to be the result of that shockwave traveling through the interior and converging on the far side. The impact hit so hard that it left marks on the other side of the Moon. And yet, Mimas survived. It held together. It continues to orbit Saturn, carrying this enormous scar on its face. Mimas was long considered a geologically dead world. No internal heat, no activity, just a battered ball of ice, slowly orbiting Saturn. But in 2023, scientists analyzing data from Cassini's long observational record published a study that suggested something unexpected. Mimas appears to oscillate as it orbits Saturn in a way that is not easily explained by a simple, solid interior. The oscillations are subtle, tiny variations in how quickly Mimas rotates relative to its orbital position, but they are real. And one possible explanation is that Mimas, like Enceladus, has a liquid water ocean beneath its icy surface. If confirmed, this would be extraordinary. Mimas shows no surface signs of geological activity whatsoever. No plumes, no tiger stripes, no fresh terrain. Its surface is heavily cratered, suggesting it hasn't been reshaped in a very long time. And yet, its interior might be liquid. If Mimas has a subsurface ocean, it may be the youngest ocean in the solar system recently formed, not yet old enough to have melted through the ice and changed the surface. An ocean that only recently came into existence, hidden beneath a cratered, dead-looking shell of ancient ice. This would mean that ocean worlds with liquid water hidden beneath their surfaces, are even more common in Saturn's system than we thought. Not just Enceladus, with its obvious geysers, but perhaps Mimas too, quietly harboring an ocean without telling us. The solar system keeps finding ways to surprise. There is another moon worth lingering on, Iapetus. Iapetus is one of Saturn's stranger moons, and Saturn's moons have a high bar for strangeness. Iapetus was discovered by Giovanni Cassini in 1671, the same astronomer who found the gap in the rings. He noticed almost immediately that it was odd. When Iapetus was on one side of Saturn, he could see it clearly. When it was on the other side of its orbit, it effectively disappeared, too faint to observe. The explanation took years to understand. Iapetus is tidally locked to Saturn, meaning the same face always points towards Saturn as it orbits. And the two hemispheres are dramatically different in appearance. The leading hemisphere, the one facing in the direction of Iapetus's orbital motion, is covered in extremely dark material, one of the darkest surfaces in the solar system. reflecting only about 3 to 4% of the light that hits it. The trailing hemisphere, facing in the opposite direction, is covered in bright water ice and reflects most of the light that hits it. The two hemispheres are so different that Cassini, in the 1600s, proposed that Iapetus must have one dark side and one bright side. He was correct. But the reason wasn't understood for centuries. The leading hemisphere is dark because as Iapetus moves through its orbit, it sweeps up dark material, dust and debris that is drifting inward from Saturn's outermost known ring, the Phoebe ring. The Phoebe ring is an enormous, diffuse ring made of dark material knocked off the moon Phoebe by small impacts. As Iapetus orbits, it plows into this material. The dark dust accumulates on the leading hemisphere over millions of years. Then, because the dark material absorbs sunlight more efficiently than the surrounding ice, the dark regions warm up during the long Iapetus day. The ice in those regions sublimates, evaporates directly from solid to vapor, and migrates to the colder trailing hemisphere, where it refreezes. This creates a feedback loop. Dark areas get darker as ice leaves them. Bright areas get brighter as ice accumulates. Over millions of years, the contrast between the two hemispheres is amplified dramatically. Iapetus did this to itself. The dark leading face and the bright trailing face are the result of dust accumulation and a runaway thermal process operating over geological timescales. But there's another feature of Iapetus that has no fully satisfying explanation. Iapetus has a mountain range running almost exactly along its equator. A ridge of peaks stretching for over 800 miles, reaching heights of around 12 miles in some places. 12 miles high. Nearly twice the height of Mount Everest, above sea level. These mountains sit precisely on the equator, dividing the moon into northern and southern hemispheres like a seam on a tennis ball. Where did this ridge come from? No other moon in the solar system has anything quite like it. Several hypotheses have been proposed. One is that the ridge is a remnant of an ancient ring system around Iapetus itself, material that once orbited Iapetus in a ring around its equator and eventually fell down onto the surface in a thin band. Another hypothesis is that the ridge is a remnant of when Iapetus was spinning much faster in the past, a shape that the solid crust locked in as the rotation slowed down. Neither explanation is fully satisfying. The equatorial ridge of Iapetus remains one of the genuine mysteries of the Saturn system, a feature that exists, that we can measure, that we have visited with cameras, and that we don't fully understand. Saturn does that. Every time you think you've accounted for all the strangeness, it produces another one. Returning to the rings for a moment. Because there is a feature of the ring system that deserves more attention than it usually gets. Saturn's rings are not simply a flat disk of uniform material orbiting the planet. They are extraordinarily structured. The Cassini spacecraft, during its 13 years in orbit, revealed that the rings contain waves, not metaphorical waves. Physical waves, spiral density waves, and bending waves propagating through the ring, material like ripples across a pond. When a moon is in orbital resonance with a region of the rings, when the ring particles and the moon have orbital periods in a simple ratio, the moon's repeated gravitational nudges at the ground, same orbital position, push and pull the ring particles in a coordinated way. This creates a spiral wave that winds outward through the ring like the groove on a vinyl record. Thousands of these wave patterns thread through Saturn's rings. They carry information about the mass distribution in the rings and about the resonances that drive them. By studying the wavelengths and amplitudes of these waves, scientists have been able to measure the mass of individual ring regions and constrain the density of the material. But more remarkably, some waves in the rings appear to be driven by oscillations inside Saturn itself. Just as earthquakes on Earth send seismic waves propagating through the planet's interior, Saturn appears to have internal oscillations, waves inside the planet, and those oscillations couple to the ring system through gravity. The rings vibrate in response to Saturn's internal heartbeat. This technique, using the rings to study Saturn's interior, is called ring seismology, and it has revealed things about Saturn's internal structure that no other method could access. The nature of the fuzzy core, the way different layers of the interior rotate at different rates, the density profile of the metallic hydrogen layer. All of this extracted not from any instrument inside the planet, no instrument could survive there, but from the careful measurement of wave patterns in a disk of ice particles orbiting the planet from the outside. The rings are not just a decoration. They are a scientific instrument. The most sophisticated gravitational seismograph ever built, constructed not by any engineer, but by physics itself over millions of years. And Cassini was the tool we used to read it. By tracking the spiral waves threading through the ring material, Cassini's instruments gave us a window into the interior of a world where no probe could ever go. The information was encoded in ice, written in the language of orbital mechanics, and decoded by scientists on Earth. It is one of the most elegant pieces of indirect measurement in the history of planetary science. And it all depends on the rings existing in the first place. On some object, hundreds of millions of years ago, coming a little too close. On Saturn's gravity, tearing that object apart. On the debris spreading into a flat disk and grinding itself into the smooth, thin sheet of ice we see today. The catastrophe that created the rings also created the instrument that is telling us the secrets of Saturn's interior. Violence, in the end, producing understanding. And consider what it is like to fly through the ring system, even conceptually. The main rings span roughly 170,000 miles in width. At the orbital speed of particles in the outer A ring, those particles are moving at around 38,000 miles per hour. At the inner edge of the B ring, the speed is around 58,000 miles per hour. Every particle in the ring system is moving at a different speed, orbiting according to Kepler's laws, closer particles faster, farther particles slower. Within the rings, collisions between particles happen constantly. The mean free path, the average distance a particle travels before hitting another particle, varies enormously, depending on which region of the rings you're in. In the dense B ring, collisions are frequent. In the Cassini division, much rarer. The collision dynamics within the rings are complex. Particles can bounce off each other, stick together, or shatter, depending on the relative velocity of the collision and the composition and size of the particles involved. In the outermost parts of the A ring, there are clumps, temporary aggregations of ring particles that form and break apart continuously under the influence of self-gravity and collisions. These clumps can be hundreds of feet across, forming briefly before being disrupted by a collision or by tidal forces from Saturn, then reforming somewhere else. The ring system is not static. It is dynamic. It is alive in a physical sense, constantly churning, constantly evolving, losing material to the planet below and to space above, shaped by dozens of moons and by oscillations from within the planet itself. It is one of the most complex physical systems in the solar system. And it is going to be gone. Not tomorrow. Not in 1,000,000 years. But gone. The beauty you see when you point a telescope at Saturn tonight is borrowed beauty. Borrowed from a past when an object, perhaps a moon, made the mistake of coming too close, and slowly being repaid to the planet below. There is something else about Saturn that belongs in a conversation about why it's genuinely daunting. It's the time scale. Saturn has been there for 4.5 billion years. It formed from the same cloud of gas and dust as the Sun and everything else in the solar system. But while Earth and the other inner planets were being blasted by impactors, while the surface of early Earth was a magma ocean, while life was just beginning to experiment with chemistry in shallow Archean seas, Saturn was already essentially what it is today. A gas giant, rotating in roughly 10 hours, probably already generating its metallic hydrogen and its magnetic field, probably already forming moons from the material orbiting around it, already enormous, already indifferent. Saturn was ancient when the first cell divided on Earth. It was ancient when the first multicellular life evolved in Earth's oceans. It was ancient when the first animals crawled onto land. It was ancient when the first tree grew. It was ancient when the first human looked up at the night sky and wondered what that bright point of light was. And during all of that, during every one of those billions of years of biological history on Earth, from the first self-replicating molecule to the first creature to ever wonder about the world around it, Saturn was there, rotating, generating its winds, raining helium, hosting its moons in their orbits, losing its rings 1 second at a time. It noticed none of it. It recorded none of it. It was simply there, doing what a gas giant does, indifferent to whether anything anywhere was watching or wondering or writing about it. The Babylonians who first kept records of Saturn's movement across the sky, those astronomers who built clay tablets, predicting its position years in advance, they were the first humans to pay sustained, systematic attention to this planet. That was roughly 2,600 years ago, which is to say, humanity has been attentively watching Saturn for about 0.06% of Saturn's existence. For the other 99.94% of its history, it was there and we were not. Or we were not yet complex enough to notice. Or we did not yet have the tools to do anything useful with the noticing. The history of our relationship with Saturn is a history of technology slowly catching up to curiosity. First, the naked eye tracking a bright wanderer across the sky. Then the telescope, revealing the rings. Then the mathematical tools to predict its motions precisely. Then the spacecraft to actually go there. Then the instruments sophisticated enough to sample its moon's oceans from the inside. And now, the mission's being planned to go back, with better tools, with more precise instruments, with questions that only Cassini's discoveries made it possible to ask. Every generation has looked at Saturn with the best tools available and come away with something new. Every generation has also come away with new questions that their tools couldn't answer. That pattern is not going to end. Saturn is deep enough, complex enough, surprising enough, that no single generation of scientists and spacecraft is going to exhaust it. It will still be producing new discoveries long after the people reading about it today are gone. And that is, in some way, one of the most comforting things about Saturn. It is inexhaustible. Whatever we find, there will be more. And it will be there, waiting not with any intent, but simply by existing for the next question we're able to ask. When the sun becomes a red giant and swells outward to engulf the inner planets, Saturn will still be there, farther from the expanding sun's new boundary, possibly still with some of its moons intact, still turning, still raining helium into its own interior. No one will be there to see it, but Saturn will not notice. It simply will be. That kind of timescale, that kind of permanence, is part of what makes Saturn so hard to fully absorb. We exist for a moment. Saturn's storms exist for months. Its rings exist for hundreds of millions of years. The planet itself has existed for 4.5 billion years, and it will exist for billions more. Every time you look at it, you're looking at something that has been there since before any life existed anywhere on Earth. And it will still be there long after the last living thing on Earth is gone. That is not frightening in a visceral way. It is frightening in the way that really deep truths about the universe are frightening. It changes your sense of proportion. It asks you to see yourself not as the center of things, but as a brief, minor visitor. And Saturn, glowing golden in the night sky, is perhaps the most beautiful and most confronting reminder of that the solar system offers. Let's talk about Saturn's magnetosphere, because it is a remarkable environment in its own right. Earth has a magnetosphere, a region of space where Earth's magnetic field dominates the behavior of charged particles. The magnetosphere deflects the solar wind, the continuous stream of charged particles blowing outward from the sun. Without it, the solar wind would steadily erode Earth's atmosphere over geological timescales. Saturn has a magnetosphere too, and it is enormous. Saturn's magnetic field is about 578 times stronger than Earth's at the surface. The magnetosphere it creates stretches roughly 65 Saturn radii, about 2.4 million miles, out toward the sun on the sunward side. On the far side, away from the sun, it stretches even farther out to tens of millions of miles, forming a long tail in the solar wind, like the wake behind a boat. Inside this magnetosphere, charged particles are trapped. Protons and electrons spiral along the magnetic field lines, bouncing back and forth between the north and south magnetic poles. These trapped particles form radiation belts, rings of high-energy radiation encircling Saturn, analogous to Earth's Van Allen belts, but far more intense in some regions. The rings interact with these radiation belts in a complex way. The ring particles absorb some of the high-energy particles, clearing out zones in the radiation belts. Conversely, the high-energy radiation breaks down the surface chemistry of ring particles, contributing to their darkening over time. The magnetosphere is also fed by material from Saturn's moons, particularly from Enceladus. The plumes of Enceladus release water vapor and ice particles into space, and much of this material is ionized by solar ultraviolet radiation and trapped in Saturn's magnetic field. It forms a vast torus of plasma, a ring of charged particles orbiting Saturn at roughly Enceladus's orbital distance. This plasma torus extends outward and becomes part of Saturn's magnetosphere. Enceladus, a tiny moon 300 miles across, is one of the primary sources of material for Saturn's enormous magnetospheric environment. The interactions between the plasma torus and Saturn's magnetic field generate complex electrical currents flowing between the moons and the planet's upper atmosphere. Cassini mapped these current systems in detail. They produce aurora, shimmering curtains of light near Saturn's poles, where the currents feed energy into the upper atmosphere. Saturn's aurora are primarily ultraviolet and infrared, mostly outside the visible spectrum, but they are real, bright, and complex. They pulse and shift with the dynamics of the magnetosphere. When the solar wind strengthens during periods of intense solar activity, the aurora respond brightening, shifting to higher latitudes, changing their structure. Saturn's poles are never quiet. The magnetosphere is constantly being disturbed by the solar wind, by the material from Enceladus's plumes, by the electrical currents from the moons. The aurora are the visible signature of all that activity at the boundary between the magnetosphere and the atmosphere. Another thing Saturn's magnetosphere does, which is not widely appreciated, is protect the moons within it. The inner moons, Mimas, Enceladus, Tethys, Dione, Rhea, all orbit within Saturn's magnetosphere. They are shielded from the direct impact of the solar wind. The solar wind never reaches them. Instead, they exist in a relatively stable plasma environment, dominated by Saturn's magnetic field and the particles from Enceladus's plumes. This has implications for habitability. If Enceladus has life in its ocean, that life is doubly protected by the ice shell above the ocean and by Saturn's magnetosphere above the surface. The solar wind, with its energetic particles that can damage DNA and break apart complex molecules, never reaches Enceladus's surface directly. Saturn is, in this sense, a shield for its moons, an enormous magnetic umbrella sheltering the worlds in its system from the harshest effects of space. One last piece of Saturn's story that rarely makes it into the popular summary is the planet's role in defining our understanding of planetary formation. Saturn is not just an object to be studied, it is a test case, a benchmark against which our theories of how planets form and evolve are measured. When astronomers study planets around other stars, exoplanets, one of the most common types they find is what's called a hot Jupiter, a gas giant planet orbiting very close to its star, much closer than Mercury is to the Sun. This was one of the great surprises of the early exoplanet era. The leading model of planetary formation suggested that gas giants should form far from their stars, in the cold outer regions where the building material, ice and gas, is plentiful. Then why were there so many gas giants orbiting close to their stars? The answer, developed over years of theoretical work, involves planetary migration. Gas giants can form in the outer part of a solar system and then migrate inward, moving closer to the star over time, due to interactions with the disk of gas and dust they're embedded in. This migration can carry a gas giant all the way from the cold outer reaches of a system to a tight orbit around its star. Jupiter and Saturn, in our solar system, may have migrated as well. There is a hypothesis, sometimes called the Grand Tack model, that suggests Jupiter first migrated inward toward the Sun and then turned around and migrated outward when Saturn formed and became locked in a gravitational resonance with Jupiter. This inward, then outward migration of Jupiter, guided by its interaction with Saturn, may have shaped the architecture of the inner solar system. It may have cleared out material that would otherwise have accumulated in the inner solar system, leaving the inner planets smaller than they might otherwise have been. It may have scattered material into the asteroid belt and the Kuiper belt. It may have influenced the late delivery of water and organic molecules to Earth. The details are still debated. The Grand Tack model has been challenged and refined over the years. But the core idea that Saturn's formation and its gravitational interaction with Jupiter shaped the entire inner solar system is taken seriously by planetary scientists. Saturn didn't just form in the outer solar system and stay there. Its formation changed the environment for everything inside it, including the formation of Earth. The planet we live on may have the shape and size and composition it has, partly because of Saturn. The water in our oceans may have arrived here, in part because of how Saturn's gravity influenced the delivery of water-bearing objects to the inner solar system. The size of Mars, smaller than most planetary formation models would predict, without the influence of Jupiter and Saturn, may reflect the clearing of the inner solar system by those two giants. Saturn's history is written into the architecture of the solar system, and the architecture of the solar system is written into us. We are made of elements, forged in stars that lived and perished before the sun was born. We exist on a planet whose size, composition, and water content were shaped in part by the gravitational influence of a gas giant nearly 1 billion miles away. And we have the extraordinary capacity to figure that out. The story of our relationship with Saturn is also a story about human ambition. In the 1960s and early 1970s, the Apollo program was consuming the attention of the world's most ambitious space thinkers. Sending humans to the moon was the great challenge of the era. But even as that program was underway, a group of engineers and scientists at NASA were planning something that had never been done before. They wanted to send spacecraft not just to the moon or to the nearest planets, but to the outer solar system, to Jupiter, Saturn, Uranus, Neptune. Worlds that no spacecraft had ever visited. The challenge was enormous. The distances were so great that the spacecraft would need years just to reach their destinations. The power sources available at the time, solar panels, would be useless that far from the sun, where the light is a fraction of its intensity at Earth. The spacecraft would need nuclear power sources, called radioisotope thermoelectric generators, that convert the heat from the natural decay of plutonium-238 into electricity. Reliable, long-lasting, not dependent on sunlight. And the communication delays would be significant. By the time Voyager reached Saturn, the signal delay was over an hour each way. Every command sent from Earth would take over an hour to arrive. Every response would take over an hour to return. The spacecraft had to be largely autonomous, capable of executing pre-programmed sequences without constant guidance from Earth. And yet, despite all of this, Pioneer 11 reached Saturn in 1979, Voyager 1 in 1980, Voyager 2 in 1981, 3 spacecraft. 3 successful encounters with a planet nearly 1 billion miles from Earth, using technology that, by modern standards, was extraordinarily limited. Voyager 1's computers had about 69 kilobytes of memory. A single modern smartphone has more computing power by a factor of millions. And yet, those spacecraft navigated to Saturn, photographed its rings in detail, discovered new moons, measured its magnetic field, and sent the data back across the solar system on a radio signal so faint that it required some of the largest antenna dishes on Earth to detect. This is one of the things that Saturn does to you, if you let it. It makes you appreciate what human beings are capable of. Not just the scale of the universe and our smallness within it, though that too, but the audacity of reaching out into that scale and actually touching it. actually sending a machine to a world 1 billion miles away and getting useful science back. Cassini was a product of that same audacity. 27 countries contributed to the mission. Thousands of scientists and engineers worked on it over more than 2 decades, from conception to end of mission. The spacecraft itself weighed about 6 tons and carried 12 scientific instruments. Its grand finale, those final 22 orbits between the rings and the planet, produced some of the most precise measurements of Saturn's gravity, magnetic field, and ring composition ever made. In the last few weeks, before its final plunge, Cassini was doing science that had never been possible before, flying through the ring plane, tasting the upper atmosphere, measuring the mass of the rings more accurately than ever. Up until the very last second, it was working, transmitting, doing science. And then it was over. And the solar system had 1 fewer active spacecraft and 1 more fragment of human engineering dissolved into the clouds of Saturn. When you step back and consider everything: the winds, the hexagon, the rings, the moons, the metallic interior, the helium rain, the ring seismology, the hidden ocean of Enceladus, the methane seas of Titan, the equatorial ridge of Iapetus, the young ocean possibly hiding beneath Mimas, the planet's role in shaping Earth's history. What you're looking at is not just a planet. You're looking at a system. A complex, interconnected, self-consistent system of physics. The planet generates a magnetic field that funnels ring material into its atmosphere. The rings shape the planet's tilt through resonance with Neptune. The moons carve gaps in the rings and leave gravitational fingerprints in the ring structure. The rings rain down on the planet and are slowly consumed. The planet's internal oscillations propagate outward through the ring material and can be detected as waves. The planet's tidal forces heat some moons, driving geological activity and maintaining liquid water, oceans. Those oceans vent material into space, contributing to the ring system. It is a system where every component influences every other component. And all of it is powered, ultimately, by the same thing that powers everything: gravity. The gravity that pulled a cloud of gas and dust together 4.5 billion years ago. The gravity that squeezed hydrogen until it became metallic. The gravity that made helium droplets fall toward the center. The gravity that holds the rings in their flat plane. The gravity that keeps the moons in their orbits and locks some of them into tidal resonances. The gravity that shaped the Cassini division and the thousands of wave patterns threading through the ring system. The gravity that draws in the ring rain. The gravity that, billions of years ago, may have captured a wandering object, drawn it past the Roche limit, and torn it apart to make the rings. Gravity is the architect. Saturn is the result. And the result, on every scale, from the individual particles grinding together in the rings to the planet-girdling storms, from the hidden oceans of frozen moons to the metallic hydrogen flowing thousands of miles deep inside the planet, is extraordinary. The night sky gives us no real indication of any of this. Saturn is just a bright dot moving slowly against the stars. It takes a telescope to see the disk, a slightly better telescope to see the rings, and a spacecraft, years in transit, to begin to understand what's actually there. This is true of almost everything in astronomy. The universe hides its nature from casual inspection. You have to work to see it. You have to invest time, equipment, curiosity, patience to get past the surface appearance and into the reality underneath. Saturn is a particularly striking example of this principle. It looks calm. It looks serene. It looks like the kind of thing you'd put on a poster for a children's bedroom. Gentle, beautiful, unthreatening. And then you learn about the winds, and the storms, and the metallic interior, and the vanishing rings, and the hidden oceans, and the moon with an equatorial ridge nobody can fully explain, and the moon that looks geologically dead but may have a liquid ocean inside, and the spacecraft that studied it for 13 years and then fell into it. And suddenly, the poster in the children's bedroom looks different. It looks like the surface of something much deeper, a window into the kind of reality the universe actually consists of. Not gentle, not serene, but extraordinary. Complex beyond any simple description. Violent and beautiful simultaneously. Old beyond any meaningful human comprehension. And indifferent to whether anyone ever understood it. Saturn has been there for 4.5 billion years. It will be there long after every telescope that has ever pointed at it has turned to dust. And it will keep doing what it has always done, rotating in roughly 10 hours, generating its winds, raining helium into its own interior, losing its rings 1 kilogram at a time every second of every day, keeping its oceans hidden, throwing its atmosphere into hexagons and planet-girdling storms, being, in every way, exactly what it is. The scariest planet in the solar system, hidden behind the most beautiful face in the solar system, waiting for the next person who looks closely enough to see both at once. Thanks for staying with me through this one. The solar system has no shortage of wonders, but Saturn occupies a place all its own. It is the planet that shows you beauty first, and only slowly, if you look closely enough, reveals the extraordinary violence and strangeness underneath. Keep looking closely. There is always more.